All right, excellent. All right, so today we are going to talk about side channels. I guess before we get started, I didn't get a chance to respond to a bunch of you, but if you posted about turning in the assignment and all that stuff, all is good, right? Like we're not going to punish you for having something a couple minutes late. That'd be silly and defeat the point of you doing all that hard work. And I owe a bunch of you replies, but I've been dealing with a bunch of stuff at home, so I'll try to get back to you as soon as possible. But today, let's have some fun. So today we're going to talk about side channels. And just to set up the context, right? Last time we talked about isolation, different kinds of isolation, process isolation, VM isolation, even within a process, kind of library isolation, right? And this is key to actually building secure systems. So when you're building secure systems, this is one of the things that you have in your toolbox. In the assignment we just released last night, you'll get to play with using isolation and sandboxing to build a secure app from an untrusted library. And we already talked about one way that isolation can go wrong, or how you can kind of defeat systems that rely on isolation, and that's basically confused deputy attacks. So when we cross the isolation boundary, if we didn't properly check things, we're totally hosed. And you're gonna do that in your assignment and actually play with those kinds of confused deputy attacks, right? But kind of if we step back and what is isolation really giving us? Well, basically the whole premise is that it gives us a box where we can put our sensitive or secret stuff, and we can make sure that you can't get at this information other than through controlled interfaces. Right. So our assumption is that we know these trust boundaries and we know how things are accessed, so that we can actually draw this sandbox boundary to place things. But the other assumption is that there's no way for us to actually bypass this trust boundary to get at the secret stuff contained within that boundary. And you can use this trust boundary the other way around, where the secrets are outside the boundary, but it doesn't matter too much. Okay, so for this class, at least this lecture, we're going to assume that the secrets are within the secret box. So how are we going to get at data that's contained within one of these isolation boundaries? Well, we already talked about one way to do it, which is find a bug in the runtime and ideally make a call across the boundary to exploit one of these bugs. We saw or briefly talked about seccomp basically helping you address these class of attacks for at least the Linux kernel, right? So the Linux kernel exposes a huge attack surface, right? These are your 900 or something syscalls. And as an attacker, I can call any of them. If any of them are incorrectly implemented, I can totally own you, right? So that's one way I can get to the secrets. In this case, the secrets contained within the kernel. The other reason this is possible is, again, this is hard to get right, and you hit these confused deputy attacks. And one of the things that I want to encourage you is go look at the Linux kernel or any interesting runtime and try to find these confused deputy attacks, the ones that you'll be exploiting in this week's assignment. And if you do, we can give you extra credit or VAL PA grades and things like that. So finding real things in real systems is a great way to boost your grade, but also learn a lot of really fun stuff. Okay, the other one is, well, you can find a hardware bug, right? And kind of if you have a hardware bug, well, the hardware sits at the lowest layer. Usually we actually trust the hardware. And if there is a bug in hardware that lets us bypass these abstraction boundaries, this isolation boundary, then again, I can use that as an attacker and completely violate whatever assumptions that you made about this being a good software defense layer. What we're going to look at, so we're going to look a little bit at one of the hardware style bugs, but what we're going to spend most of our time today is on side channels. And right, side channels are really interesting because when we think of systems, these slides have not been posted. I didn't get a chance to do that. When we think of systems as black boxes, right? We have some abstraction, some box that consumes input and produces output. Side channels are interesting because they violate our assumption that all the side effects about this box or what's happening in the box are not visible, right? So we assume that basically all effects about output, like the values in memory or I/O, are things that can't be generally observed. observe some other way. Sorry about that. Right. So, well, okay. So we spend most of our time just thinking about how to ensure that information is not revealed across these trust boundaries, but we're not actually thinking about how information is revealed in how the computation is actually being done or how this output is being produced, right? So most of the time we're like, okay, if the output doesn't leak anything, if it doesn't leak our secret, then there's no way it could have leaked anything about what's going on inside the box. But if we have some way of observing like what was actually happening inside the box and how that output was produced, we might be able to actually infer some information. Right. So for example, how long a computation might take, how fast it is, how loud it is, how hot it is, right? These are all kind of artifacts of implementations, not the abstractions that we think about when we build software. And all these things can potentially reveal interesting information to us, right? So these are what we would call side channels. So they're basically communication channels or sources of informations beyond the explicit, concrete channel of communication, right? So our output channel is a direct, not side channel. So if we learn information through some other means, we would by definition consider that thing a side channel, right? So like how much energy your CPU uses when it performs, say, an encryption operation could potentially leak information about the secret that's used to perform the encryption or the contents of that message. Okay, so what we're going to look at today is almost like a laundry list of side channels just to get you inspired to like look at these things in the real world and maybe, I don't know, pursue one of these as like a research projects because they're actually pretty fun. Sorry. Then we're going to look specifically at cache side channels and briefly at consumption channels. And then we're going to look at how we address these cache side channel attacks with constant time programming. And we're going to end with specter attacks, which are kind of some of the most interesting hardware-based attacks that use side channels to leak information and essentially bypass all the isolation mechanisms we know of today. Okay, so what is a consumption side channel? And I want to start with the simplest possible example here, which is a password checker. So suppose I'm implementing a password checker and I'm doing it in C. So I have int check password, and this basically is just a wrapper around stir compare that compares my static password here against whatever the attacker or any user might provide, right? So how long does this password check take? Like if you like I'll leave it underspecified just to see like what you're thinking about when I ask this. Okay, so something proportional to the length of the password. This is very much like a theoretician. ON. All right. You're all right. It is ON of some sorts. But we're in the side channel lecture, so we're talking about implementations, not abstraction. So like, okay, so proportional to the number of correct characters. Yeah, so that's the most precise one. Right. So like basically this stir compare stops when it detects that the buff or the character in buff doesn't match one of these characters. So when it doesn't match, it just terminates early and stops. Right. So it doesn't actually go up to the length of this password or the length of the buff if it's different. Right. It just stops whenever the buff and the password buffer diverge. Right. So like, how can we use this as an attacker? Well, if we just supply one character at a time and measure how long it took for this thing to return, we can learn some information. In particular, we can learn whether or not we got that character right and keep going. Right. So like this is a more general side channel. It's just largely about how much of a resource is being used to perform a particular operation, right? So like in this particular case, what we are looking at is how long it would take for you to perform that password check. But another thing you could do is you could potentially measure the amount of power the thing just used up. You can measure how much memory a computation might use. You can measure how much network or how many packets it sends on a network, or what is the size of those packets. Right. And some of you may have seen, there were changes, at least say in Android, and I think even iOS, where we were exposing power information and battery information to applications. It turned out this was a bad idea because it leaks potentially secret information about other computations, and the way it does that is essentially just by abusing this power consumption channel. Okay, right. So like basically every computation uses some kind of resource, and whenever it does this, because it's a physical thing at the end of the day, there's some out of bounds signal that's generated in the course of performing this operation. Right. So for example, our computer runs, so we have some electromagnetic radiation that's being produced. The sound of your computer and what might reveal some information about what you're computing. The sound of your keyboard when you type might reveal some information about the characters that you're typing, movement in a room, error messages, so on and so forth, right? So computations have all kinds of side effects that we don't think about. And this is where attackers get clever and use those side effects to learn secrets about our computation. One really classical example is the password verification in the 10x operating system that was discovered by Alan Bell in 74. This was basically doing a character at a time comparison, and because of virtual memory, one thing that you were able to do, or at least what Alan Bell did, was align the password that you're providing to the password checker on page boundaries, such that guessing that character right leads to fetching a new page. Otherwise, it doesn't. And by detecting whether or not a new page was accessed, you can learn something about this password. I describe this at a super high level, partly because the assignment that you're going to get next is actually carrying out this attack. So it's really fun. This was a real thing, so you'd be replicating something from 74, but still pretty relevant, because these kinds of attacks actually happen or are basically happening again, but they're happening in a slightly different context. If you've heard of trusted execution environments, and I briefly mentioned them last time, they have similar kinds of attacks on them that, if you're clever about where you're aligning pages, you might leak some information about what computation is running within this box. Okay, what's another example? So, okay, that one was, we talked about timing. We talked about page tables, or whether or not things actually trap. Another one is just power, right? So secret cryptographic keys are, say, maintained in hardware, and you might not be able to actually get at memory directly or mess with page tables and things like that, right? So on my phone, I have a SIM card. This SIM card has a burned cryptographic key in it. So I'd like to try to figure out, okay, how do I actually recover this key? Well, it turns out there's like different analysis techniques. SPA is a super old one. It's simple parallel analysis. The more powerful one was invented by Paul Kocher, who kind of is one of the grandfathers of side channel attacks. But the basic idea is we're going to use signal processing techniques, right? So like machine learning on lots of samples. So we're going to like run this encryption algorithm many times with different inputs. And then we're going to essentially try to figure out, like what is that secret key based on power measurements. So on the right here, we have scopes. So an oscilloscope measuring the power output of one of these chips. And, over like thousands and thousands of measurements, you can kind of figure out that like, this signal is a 0, that is a 1. And if we run it over many different inputs, we can recover the whole key. And this is actually something kind of interesting. So like if you also just have like a power or hook up a oscilloscope to even your outlet, there's a bunch of things that you can pick up, because your house is essentially like a giant antenna. So EM radiation from around is actually leaked and picked up by your house. You should totally not do this unless you become, an EE and know what you're doing. But it is a thing. Something maybe closer to home is keystroke timing leaks that happen over the network. So when you're using SSH, this was a pretty clever attack by Don Song, Dave Wagner's group at Berkeley. But the basic idea was like, hey, we have SSH. When we SSH into a box, we don't want to send a bunch of packets, then have the shell reply back with like whatever we just typed, right? Like we want to have a really quick interactive response from the server. And what this basically means is whenever we type a character, it immediately goes over the network, right, to the server. The server echoes it back, right? So this is kind of happening because, and we want this for our user interface. We don't want to batch these things, which is what you normally do. So what this basically means is if you're a network attacker, right? So if I'm sitting in your dorm room or wherever, and I have the ability to sniff network packets, I can measure just the time it takes for these packets to be sent over. And it turns out that when you type things, you're actually you have a distinct typing pattern. So usually, like typing, Julia, as we have in this particular example, might be very different from your typing, Julia, is kind of different from mine, but we still share some underlying structure of how we actually generate these words. So if you have, say, the English alphabet, you can generate timing patterns for humans, and from that recover what somebody typed over the network. So, and this attack is used not just over the network. You can use it with sound recording of somebody typing. This is why I don't type my password in class, or when I do, I try to mute myself. Because you could pretty easily recover my password just from how I'm typing things. Okay. In their case, it was particularly interesting because things like typing in su, right, to take on the root shell is pretty distinctive because it's su and then return, and then it's typically the password. So like you can kind of figure out what the root password is by just watching the network. Okay. Something closer to home, I guess, physically is stuff that was happening at UCSD. So this started in 2010 when kind of our security and PL group was looking at history sniffing attacks. So basically, your browser, as you may have seen, when you visit a particular website, it might highlight it in purple or in blue. And back in 2010, it would let you, actually inspect the color of a particular link. So what this meant is, as an attacker, as a web attacker, and we'll get into web attacks next week, you would be able to just kind of insert links into the page and check what the color of those links are. And based on the link, you know whether or not this person that visited your website visited a particular different website, right? So like if I visit, NewYorkTimes.com, NewYorkTimes.com can figure out whether or not I visited all these other pages by just looking at the color of links that, are not even visible to you as the user at the page. You can do all of this in the background. So since then, there was actually a huge response to this paper, and browser vendors kind of fixed this. So now it turns out that if you want to write JavaScript to inspect or change the color of links, that's way, way trickier. You can't actually do that. But there are side channels for doing this. So what we were looking at in 2018 is browsers have all these new fancy features, and they let you have CSS 3D transforms. And what this actually means doesn't really matter. I don't even remember, to be honest. Michael, the student that ran this attack, it's pretty fancy. But what it essentially lets you do is, whether or not a link has been visited, it lets you perform this 3D transformation or not. And whether or not you perform this thing actually affects the rendering time of that particular link. And if you can measure that thing, that leaks whether or not this transform was applied or not, which basically tells you whether or not you visited that link or not, right? So even a decade later, what we found out was that these history sniffing attacks are still possible. Right, and there are all kinds of different vectors, and you're likely to see at least one or two more papers in the next year or two on this exact thing. And this is scary because which website you visit tells a lot about a person. Okay, the other kind of example of it started in 2014, and then a bunch of years later they demonstrated this attack again. This is the case of having or just being even in a separate room and listening to just acoustic noise, you're able to figure out what the person in the other room was typing. There's really cool videos of this, so I would just recommend just Googling, and you'll see really cool videos from folks in Europe carrying out these kinds of attacks. Going slightly further out, again, cross-room attacks were done on image displays that were basically just emanating radiation. So this is more like old school displays. It's not the new stuff, but the new stuff probably leaks a bunch too. But essentially, with a really cheap antenna, you would be able, from 10 meters apart, you'd be able to recover the whole screen content. So this is pretty clever, and similar kinds of attacks, or at least in this spirit, but using lasers and pointing lasers at smart speakers, like would let you control the speaker or figure out what is being said. So it's pretty interesting. Okay, so that's acoustic. We talked about software. We talked about power. There's also just the optical domain, right? So light emitted by a CRT, right? The old school TVs and monitors is just a video signal with a response. So if you have a photosensor, you can actually separate this signal from the high frequency components, and you'd actually be able to infer what's on the screen, even if that thing was actually reflected. So for example, one of the attacks that they demonstrated is like, here's this thing that's being displayed on this CRT monitor, and off of a wall, you'd be able to recover exactly what was on the screen. So all of these are kind of NSA level intelligence attacks, right? So you're not likely going to see these attacks done against you unless you end up working for an intelligence community or something like that. But they are things to be worried about. So if you look at buildings that have sensitive information, like top classified stuff, then you'll see even the design of the building kind of is meant to address these style of attacks. Like they want to make sure that you can't point a laser to hear what people are talking about inside, if they even have windows, right? A bunch of these things are completely gapped to exactly address these kinds of attacker models. Okay, so from the optical, we have heat. I think we saw some version of a keypad that was worn out. Well, it turns out it doesn't have to be worn out. If you have a temperature sensor, you can kind of figure out which things were just recently pressed. And from that, you can figure out at least a subset of the keys to use to get in. Okay, so that's all I got for side channels. What I want to briefly talk about is active side channels and covert channels. So active side channels, they're essentially like things that the active bit is where the attacker comes in. So as an attacker, I may have a weak side channel that is like a side channel that's not necessarily either high bandwidth or very easy to measure. So one thing I might be able to do is flip bits during, or cause you to flip bits during a particular operation, and that might be easier for me to actually recover than trying to measure the other thing. These kind of fall into a category of attacks called fault injection attacks. So basically what I do as the attacker is I cause these kinds of either bit flips, or I cause glitches in power or voltage, or even your CPU clock, or even like vary the temperature of your CPU by putting a light on it, right? So like just getting it to like to flip some bits. This causes radiation. This causes the thing to do something unexpected. And at the very end, what we'll see is actually a kind of interesting attack against a voting machine, where they pointed a light at the voting machine and got it to vote the other way by injecting radiation. All right, so this is kind of like on the right side, whereas like most of the other things that we talked about is on the read or leak side. Okay, so I have one last bit on the overall kind of idea of side channels, and this is covert channels. And you might see these two words being used interchangeably. So people might say covert channel when they mean side channel. They might say side channel when they mean covert channel. So I want to just make the distinction here, and you can remember it or forget it. But I think it's an interesting distinction because one we can deal with, the other one is kind of hard. So side channels are inadvertent artifacts of the implementation that can be analyzed to extract information across the trust boundary, right? So side channels are just things that result as of my inadvertently when my computation executes, right? So I execute, then I leak some things inadvertently. You might be able to measure that leakage, however I do it, and then figure out something about, the secrets that we use in this computation. The idea of a covert channel is kind of similar, but it's done on purpose, right? So whereas normally I don't write a piece of code to leak my secret information, but if I'm in a scenario where I, as the attacker, gets a supply code, right, I may actually try to leak information through one of these side channels explicitly because I can't leak it directly. So, for example, if you have, say, a Trojan, right, so like your task is to implement a Trojan that can't be detected by the victim. How would you do it? Well, okay, like it's usually pretty hard for you to leak the information directly because that's something, if my password ever appears in a network packet, I'd be pretty paranoid and be able to detect that. But if you, vary the information, leak the information by varying, say, the amount of time it takes you to send a packet over the network, and over a long period of time, you leak my whole password. You've used this network packet delay as a side channel to leak this information, right? And again, going back to the Mossad style attacker, right? Like if you've somehow infiltrated one of these secure locations, your best bet to leak things are through covert channels. One way to do that is, for example, to mess with the HVAC system, and then somewhere else you can measure the temperature and try to figure out, what was actually sent over this side channel network. But as a defender, how do you defend against the thing? It gets really super duper hard. There's some things that we can, certain kinds of core channels that we can deal with, but in general, we can't. And kind of at some point, you have to draw the line of this is outside of your attacker model. Okay. And I guess on that note of defense, we're going to see like one particular way against timing side channels and cache side channels, of how do you actually address those. Kind of the easiest one-line summary is just eliminate any dependency on secret data. That's harder than you think. We can also try to make everything take the same amount of time, take the same amount of memory. This is also hard to do. We have explored these things, at least with CPU time and memory, but it is actually, you have to get buy-in from your whole software stack up, and you have to potentially even go into, hardware modifications if you don't trust the hardware to do things differently underneath you. So like we actually have to think about, the runtime system, the garbage collectors, your compiler, how all these things actually interact. And even when we do that, it turns out to be actually pretty expensive to do, right? So think about having to, about not leaking information through the size of the packets that you send. Well, that gets really tricky. Like, what is a reasonable packet that would include everything that I might potentially send, right? Like, is that going to be 128 kilobytes, 1 megabyte, 2 megabytes, 1 gig all the time? Because that now we're getting into time too. So it gets really tricky to do this right. And at some point you're going to be leaking something, but maybe the right thing to do is to try to figure out how much you're willing to actually leak. We could also try to hide. And one kind of approach to doing this is to perform computations on slightly random data. So instead of performing, addition on my value X, you would do it on my value X times some random factor, and then that gets pretty hard for the attacker to actually figure out what X is, unless they can figure out R, which they generally can't if we have a good random generator. This is not to say that you should add random noise. This is a thing that people think that you can do. So just adding random noise basically makes it slightly harder for the attacker, but there are well-known signal processing techniques where you can just recover the noise signal from the actual signal and then like remove it out of the whole composed signal, and voila, you're back to getting the actual data that you wanted. Okay, so I think we have maybe a way to spread out view of side channels, but there's many different ways to leak, and that's the thing that I wanted to get across. And like you could probably come up with a bunch of different ways that other people haven't thought about. In the rest of the lecture, we're going to look at cache side channels. Okay, so to do that, we want to do a little bit of a review. So first, like, what is a cache, right? So like, why don't you tell me? I'll drink some water. I've been talking too much. Yeah, okay, great. So all those answers are right? So it's it's a tiny amount of memory. It's a tiny amount of memory on top of bigger memory, and there might be an even tinier amount of memory on top of that memory, with the whole idea of like, look, like whenever we access, say, main memory, it's awesome, but it's slow, right? So like like I have 256 gigs of RAM on my machine. If I were to try to access any of these at any point, that would be pretty slow, right? But that's why we can have lots of it. What we can do to make each load and store faster is we can have smaller memories that are closer to the actual ALU where we perform these computations. And that thing caches what's in the main memory, and that cache might itself have a cache, right? So like we love caches so much that we have many layers of cache, right? So like on your CPU, you might have multiple cores. In fact, you probably do unless you're running a Raspberry Pi. Even your phones have multiple cores. Those cores have two caches. One is an instruction cache. The other one is the data cache. Those things sit in front of an L2 cache that's shared across the cores. Then the L2 cache is contained and sits on top of the L3 cache, which itself sits on top of memory, right? So things are fast here, slow here, but small and huge here, right? And our hope is to stay as close as possible to the core as we are, because that's just means our computation is faster, right? But the thing that's worth mentioning is that this is a shared resource, and because these things are small, we're going to have to actually balance that out between different programs running on our cores, right? And the L2 will be a shared resource between all the cores, right? And so is the L3, and so is memory, right? So all of these things, because they're shared resources, if I, as the attacker, gets to control how they're used, I might be able to get you to leak some information that way. Okay, before we go into how we actually leak, we should talk a little bit about how cache is organized, right? So our unit of granularity is the cache line. So this is typically 64 bytes. Cache lines are grouped into sets. Each memory address is mapped to a set of cache lines, right? So like we're going to have one, say, address here. Let me make this easier to go through. So normally when I have an address in memory, this might map to index 0 here, but so might the fourth address, and address 1 and 5 might similarly, well, okay, that was not the best line. 1 and 5 might similarly share 1, and we may have different ways of associating the cache, but kind of all those details don't really matter, at least for this high level description. The only thing that we really care about is this last bullet, which is, well, what happens when we have collisions, right? So what happens when I access 0 and then 4? Well, whatever was stored in the cache beforehand has to be evicted, right? So if we end up evicting that thing, that means that now accessing 0 the second time is going to be slower than it would have been had we not accessed 4. You've all seen this, yeah? Oh, you haven't? Okay. Well, the basic idea is we're going to end up, because the main memory is huge, we're going to end up mapping to this smaller amount of memory, and some addresses will end up colliding because we just have to make do with a smaller amount of memory, right? So you can think of this as some kind of hash function, right? Like where multiple things end up mapping to the same bucket because we only have a certain number of buckets to work with. Okay, now because I think it's okay if you haven't taken a class. This is that's all you really need to know. That there is eviction happening, and when you evict something, Now something else may take a little bit longer, and hopefully by the end you'll kind of get a gist for how these attacks actually work. Okay, so the cache is a shared system resource. The kind of decades of computing have been lying to us that all of these like awesome instruction set architecture optimizations are just performance optimizations. They're totally transparent to your program. Like your program, you don't write it necessarily to be aware of the cache. If you did, it could probably be faster, and sometimes you need to be aware of those things. But in general, when you write a piece of code, you don't think about the cache, right? It just happens that your program will be faster if it's friendly to the cache. So it's an abstraction that we don't see at the programming level. And what this basically means is that our isolation mechanisms are also unaware of this. So we have now some shared resource that's not made explicit at the isolation boundary, and we can, as with any other physical resource that's shared, learn information about anybody else that's using this shared resource, right? So like one process can learn about another process because we're both using the same cache. And we'll see how we'll do that if we were, say, an attacker trying to explicitly do this. Okay, so what does it mean to be an attacker in this case? Well, okay, so what we're going to assume is that the attacker and the victim are actually isolated. So the victim and the attacker run in separate processes or separate isolation domains, right? Like if we're within a process, they're completely separated from each other. But they're on the same physical machine. They might be, two separate VMs, two separate processes, or two separate library sandboxes, kind of looking back to the previous lecture. I, as the attacker, what I can do is I can invoke, so I can basically call any functionality or interesting functionality exposed by the victim. Right, so or I can wait for the victim to run because I know when they may run. But kind of for our attacks, we're going to assume that you can call the victim to start executing something. So what would be an example of this where like we're co-located and I can call you, the victim, to run? So where might we have, say, two different parties that are sharing the same physical machine but are in separate virtual machines? Great. Okay, so like let's start with okay, fantastic. You just gave me a bunch. Okay, so on the school computers, you all SSH into one machine, right? So Alice and Bob, which would pretend are actually students in this class, they both run their own programs on these machines. So they're sharing the physical machine, they're sharing the cache, they're sharing all the caches actually, and memory, right? So that's one scenario where we're co-located. I may be able to invoke you if you say run a server on this particular machine, right? So if you're, say, running your own web server on a shared machine, I can potentially call your web server. And if your web server is doing, say, crypto to decrypt, or encrypt packets between the client and your server, then, I got you to execute a bunch of crypto, right? Another example is, on any cloud provider, there are techniques for co-locating yourself as the attacker with your target victim. That target victim may be, say, a bank website. Again, that bank website does crypto because it needs to encrypt the communication between its server and every client. And I, as the attacker, now I'm running also, an EC2 machine on AWS, and I'm sending a request to the bank. I just got it to execute a bunch of things because we're on the same machine. I might be able to observe some things on this physical machine. Now, our hope is that the attacker. So the question is, programs running on a single core machine. I think the number, of course, doesn't honestly matter too much because we have shared caches kind of all the way down. Whether you're on the same core or separate core, you can carry out these kinds of attacks. Um, right. And kind of like our hope is that the attacker shouldn't be able to infer any contents about the victim memory. We're hoping that virtual memory actually gives us this, or if we're within the same process, something like WebAssembly or whatever other software-based techniques will ensure that you can't, as the attacker, directly um, um, access somebody else's memory, but you can mess with the cache, right? And kind of these attacks are interesting um, in scenarios where your algorithm actually has memory access patterns or control flow that depend on secret information, right? So one example of this is poorly implemented cryptography. We'll see how we implement crypto for real, but like in at least for many years, actually, we'd have encryption and decryption algorithms that would depend on secrets, and they'd access memory based on secrets, right? And if I, as the attacker, can observe these access patterns by essentially just observing what the victim is doing to the cache, then I can infer information about those secrets. And we'll see how to do this. Okay, so what can you do as the attacker, right? So how would we be able to actually start observing these access patterns? So there are a bunch of things you can do, and they're usually a combination of the verbs that we have here. So one thing you can do is you can prime the cache, right? So you can place a known address in the cache by essentially just reading it, right? So I can take some part of the cache and make sure that there's something there by just knowing the cache layout. So this is kind of an attacker assumption that we didn't talk about, but I assume that we know what the cache structure looks like. By accessing a particular address, I bring that thing into the cache from main memory, right? So the next time I access that piece of thing, it'll be fast. I can also evict things from the cache, right? So one thing I can do is you the victim placed a bunch of things in the cache by doing whatever access patterns that you did. I can make sure that those things are no longer in the cache by essentially just reading a ton of things. So I can just force a bunch of things to be loaded into the cache, and next time you access things, they'll all be cache misses. I can also just flush certain cache lines. This is not possible on all machines, but for example, on x86, you might have access to the cflush instruction that lets you flush part of the cache. And kind of those are the things that let us kind of mess with the things in the cache. The other things that we, as the attacker, can do is we can measure precisely how long it takes to perform, say, a load or a store using instructions like rdtsc on x86, right? So we typically have very fine-grained timers down to the cycle level that would let us figure out, like, okay, this load actually took a little bit longer because it went to main memory. It wasn't actually in the cache, right? So we're going to see a bunch of different attack strategies in a second, but they all have one particular form. As the attacker, what you do is you basically mess with the cache into some state that you know. Then you get the victim to run, right? So this is where we call our victim, we make a request to their server, for example, and then we measure our cache state and try to figure out if anything has changed and how it changed. And we're going to do this using three basic techniques. There are more than three. There are a bunch of other pretty cool attacks, but these are kind of the popular ones and the ones that work pretty well. So the first one is evict in time. The basic idea is we're going to kick stuff out of the cache and then see if the victim slows down as a result of this. So here, what we're doing is we're measuring victim, right? So we're measuring the victim before and after, right? So we're ideally going to measure the victim and how they would perform super well before we actually mucked with the cache, and then we're going to do it after mucking with the cache to see which part of the cache they accessed. Prime and probe, the whole idea here is we're going to put stuff in the cache, and then we're going to run the victim, but then we're going to see how we're going to measure ourselves to see if we've slowed down as a result of the victim running. So in other words, here we're measuring ourselves, and based on whether or not a particular load of store, a load is slower or faster as a result of the victim running, we'll know whether or not they touch that particular cache line. The last one is flush and reload. So here we're going to flush a particular line from the cache, and then we're going to run the victim to see if, again, our accesses are still as fast as before. Okay, so let's go through these in a little bit more detail, or just rehash, but with the actual steps. So for evict and time, the thing that we're going to do is we're first going to run a baseline measurement, and we're going to run the victim a bunch of times and measure to see how long it takes for them to perform the computation. Right, so this gives us a baseline measurement. And then we're going to actually evict part of the cache and run the victim again. And then we're going to retime them when we're doing that run. And basically, in doing so, we can figure out whether or not this second run here is faster or slower than the baseline. So if it's slower than before, then the cache line evicted by the attacker were actually used by the victim, right? So like the victim basically evicted parts of the attacker's cache lines to do their task. And what this basically tells us is some information about the addresses that were evicted by the victim, right? So we learn something about that particular program's access patterns. And sometimes these addresses can actually be secret. So for a while, AES, which is one of the standard encryption algorithms, was implemented using tables. And what this essentially meant is whatever addresses we were using, right, because we had these tables, these addresses were actually secret, and you'd be able to carry out an exact kind of evict and time attack to figure out what the AES encryption key of a separate process running on the same machine is. Okay. Do we have any questions on evict and time? All right. So I'm going to hold also a section this coming Monday so we can go over a bunch of this in more detail if we want to. Okay. The other one is prime and probe. Prime and probe works on it's pretty similar, but instead of measuring the victim, we measure ourselves, right? So the first step is we're going to prime the cache, right? And this basically means we're going to access memory locations so that previous contents, whatever they may be by the victim or somebody else, are replaced with our attacker addresses. And then we're going to do a baseline measurement of our own piece of code, right? The attacker code. And what it takes to actually access those cache lines, right? So I'm bringing things into the cache, and then immediately I'm going to measure how long it takes for me to access these cache lines. Then we're going to, again, run the victim. The victim runs, it might evict certain cache lines. And now we're going to measure, again, our own, within our own program, these cache lines that we measure in the baseline. If they're any slower, that means that the cache line was evicted by the victim, which again tells us something about the access patterns of that particular program, of the victim program. Okay, the last one is flush and reload. So flush and reload only works for if you have shared memory between, say, two different processes. This happens with like libc, for example, right? Like libc is shared memory between my process and your process on the same machine. It's also done by virtual machines. So if we're two virtual machines running on the same physical machines, sometimes the VMM or the hypervisor ends up deduplicating pages that are shared across these virtual machines. Okay, so kind of the idea here is we're going to time the memory accesses to these shared regions. And after that, we're going to flush specific lines for cache, evict the victim code, retime against the baseline, flush addresses. And again, if it's still fast, we know that it was used by the victim, right? Because they also depended on that shared memory. If it's not, then we know that we had to reload it, which means that the victim didn't actually rely on those things. right? So it's a little different from the previous two in that we're learning whether or not an address was used based on it still being fast instead of slow. But again, at the end of the day, what we learn is just something about the addresses and the memory access patterns of the victim. Okay, so now you have some idea of these cache side channels, right? So the thing that I want to point out is what we learned is addresses. Sometimes they're secret, but it doesn't seem super bad, right? Like if all you're leaking is information about addresses, you can imagine why people for a very long time didn't try to address these kinds of side channels. But it turns out that, like at least in crypto, those things leak sensitive enough information, and at least that community has decided to tackle those things. But with Spectre attacks, as we'll see at the end of the class, side channels are suddenly more interesting because Spectre lets us essentially read arbitrary parts of memory. We'll see how you do that, like across isolation boundaries, and leak that through cache side channels. So let me take this question. So Alan asks, what can we do with the leaked addresses in side channels? Can we read from them? So you can't, right? Like the only thing that we do with all these attacks is what we've learned, what was leaked was the addresses that were touched by the victim program. Now, if those addresses depend on something secret, like in the AES encryption algorithm, then you learn the secret. You learn at least part of a secret, right? You can't know the exact address. All you know is that it's that particular cache line, but that may be enough, right? So again, this is a side channel, not a direct channel. So we're not going to learn the exact contents, but if those exact contents are secret and they're used as indices into memory, we're learning a secret. So let me actually go through the constant time programming bit of the lecture, and then maybe some of these will also be clear in how they actually show up in at least crypto code. Right, so can addresses tell us anything about what is being run? So, okay, these are really great questions. Let me run through this section, and if I didn't answer both of these questions, just point it out, and we can go through it through the whiteboard. Okay, so we're going to talk about the constant time programming paradigm, which is a way of dealing with timing side channels. And here, timing side channels just basically means timing channels as in the consumption, like how long a computation takes, and cache side channel attacks. The reason I'm going to talk about these is largely because they're really good for attackers. Remote attackers can exploit timing side channels. We already talked about how if you're a co-located attacker on the same physical machine, you can abuse cache side channels to learn information, or just even a stopwatch to measure the other computation. But they're also really good for defense, right? So this is at least a class of attacks that we can actually eliminate, and we can do so with reasonable performance overhead, right? Like if we try to tackle all side channels, like we mentioned earlier, there's basically no hope of doing this in a performant way. And it's also not clear that we should, because, I don't know, EM radiation is a thing, but am I always worried about that thing? Probably not. I'm probably more worried about, JavaScript running in my browser from an attacker, or, the two of us being co-located on a physical machine on, Amazon's clouds. Okay. And to understand how we're going to mitigate or eliminate these side channels, we need to, again, introduce what introduces time variability and what actually leaks. So I'm hoping to address your questions in doing this. So to start, let's look at a very simple piece of code. It's similar to one we did before, but a little different. Okay, so here I have a function foo. This function just takes a bunch of double precision floating point values, and then iterates, I don't know, a bunch of times, however many millions that is, and performs a very simple operation. It just performs a multiplication of y, which is 1.0, and x. So the question I have for you is, does foo called with 1.0 run as fast as foo called with 1.0 to the negative 323, which is a super tiny number? Or do they take the same amount of time? What do you think? I'm very curious that nobody says B. So it's either A or C. Um, so the answer is actually A, but it might depend also on the CPU. So why do folks think that it's A? Like in the ideal world, they should take the same amount of time, right? Like that these are just instructions that go to our CPU. Our CPU, why does it care about what the value is multiplying? All right, so there are a bunch of answers. They're all um, so okay. Here, there is no compile optimization because I'm supplying that one at runtime. If the but even if I did, the compiler would have to reason about floating point, which is pretty hard. B causes overflow because it's so small. Yeah, but so what? This is all done in hardware, right? Um, well, it turns out that okay, like a bunch of your intuitions are correct, right? So just like compilers optimize things based on values for the common case. Well, it turns out that CPUs also do that, and these numbers are super tiny and basically never used. Some mathematicians will hate me for saying that, but whatever. They're called subnormal numbers, and they're super tiny, largely not used, but they're important for a floating point because we're trying to approximate the reals as much as possible, right? So these are super necessary, but not widely used, which basically means that what the CPU is doing is like, look, this I'll actually implement for real in hardware. And most of these operations on these subnormals are actually done in microcode, which is essentially software but done in hardware, right? So instead of like burning the chip to implement all of this multiplier across all possible values, we're going to look to see if these values are super small values. If they are, we essentially have a very small circuit that does this in hardware as if it's doing it in software. So microcode is basically just software, but it's software that's not exposed to us. But the CPU itself implements certain things in software, and it's basically just um, these small instructions that are used to come up with bigger instructions, right? So essentially, like for certain things like this, the CPU itself is just running software. So there's like a little interpreter, in the CPU that would be running in this case instead of having a dedicated piece of hardware doing the full multiplication. Yeah. And we can actually measure this. So like in one of the in some of the experiments that we did, we tried to see like, okay, if we feed an addition these subnormal values, are they going to take the same amount of time as everything else? Well, it turns out for a lot of CPUs, it does, but at least on these three CPUs, addition of these super tiny numbers is actually noticeably slower than addition of numbers like 1.0, 2.0. And we can look at all kinds of other operations that the CPU may perform, but just based on the number of x's here, you can see that these things are variable time and variable in the actual values, right? So like the most noticeable one is this one here, which is division of floating point numbers is very clearly going to take a different amount of time depending on the thing that you divide by. Right. So if you divide by 0, for example, this thing can be really, really super fast, right? Like there's no reason for us to go through the process of pretending to do division. But that thing is faster. It's noticeably faster than dividing by 1.0, and dividing 1.0 is still faster than dividing by 7.32 to whatever power. Okay, so these instructions introduce time variability. If the data is secret and fed to one of these instructions, the attacker might be able to actually measure this thing, right? So in this case, if we just have a stopwatch around the victim, we can potentially figure out, which things, what these secrets are by just figuring out how long it took to run this particular computation. What's the solution, right? Like we're trying to mitigate these things. The solution is to basically not use variable time instructions. we basically can't trust most hardware to tell us whether or not their instructions are constant time or variable time, or that is whether or not they depend on the actual operands. So kind of the thing to do if you're trying to build systems that are resistant to these side channels is to just not ever emit, for example, a floating point divide. There are interesting ways of still being able to do floating point division, but if you're interested in that kind of thing, we can talk offline. The one thing that I would want to point out is ARM has a really nice CPU mode, which is called data independent timing. If you enable this, then a bunch of these instructions and a subset of these instructions are guaranteed to not depend on the operands, right? So they actually guarantee that, even if this thing could have finished faster, we're still going to take the same amount as we would with other values, because we want to make sure it's not dependent on the actual operands. So this is super cool and really, really nice for us to finally have, because we need this to essentially build everything on top, right? Like if we don't have these guarantees, then the software we build on top just kind of crumbles. Okay, so timing, the data dependent timing is a problem, right? So timing variability of instructions. The other one is control flow, right? So here I have pseudocode for RSA. What it actually doesn't really matter so much, but it's a crypto algorithm, so it's dealing with secrets. And in particular, the thing that it's doing is it's branching on whether or not DI, which contains a secret bit, is 1 or 0. So if it's 1, the thing that it does is it performs this extra multiply, but if it's 0, it doesn't perform that multiply. So whether or not this thing gets executed tells me whether or not that thing was a 1 or 0, right? By just measuring this thing. So control flow is super bad. And to just highlight this, I have here a very simple piece of code. So it has 4 statements: S0, S1, S2, and S3. And depending on the secret, we execute this thing or not, right? So the way to kind of try to figure out, is this thing actually leaking some information? Well, we can just run it twice with a different secret bit, right? So if the secret is true, then we're executing S1, S2, S3. If we're saying the secret is false, then we're just executing 2 statements. And if we're going to pretend that the stopwatch gives us a nice per statement granularity measurement, then if we're measuring 4, we know that the secret is 1 or true. If we're measuring 2, then we know it's false. Yeah? Okay, so branching on secrets, also a bad idea. Now you might say, well, okay, why don't we just pad branches, right? So what we're going to do is, instead of just executing if S1, S2, and then nothing, we're just going to execute dummy instructions, S1 prime, S2 prime, that should take the same amount of S1, S2. Is this safe? Well, it turns out that this is also actually not a good idea if what we're worried about is cache attacks, right? So instructions are loaded from the instruction cache, and which instructions were loaded is actually observable to an attacker that's co-located with you, right? It's not just the data cache that can be used against you. The instruction cache can be used too, right? Right, fundamentally what's going on is we have that the hardware tried to predict where the branch grows, and whether or not that prediction is true or false is actually observable. So what can we do to not leak this thing? Well, just don't branch on secrets. So we're not going to use variable time instructions. We're not going to branch on secrets, right? But okay, now your other part of the brain is okay, so I can't use floating point divide, and I also can't branch on secrets. But okay, one seems way more serious than the other. Real code needs to actually do needs to branch. So what do we do? Well, we can turn a control flow construct like if into essentially a data flow construct like the one on the right here. So if we're, say, working with booleans, which are just 1s and 0s, then what we can turn this if secret x assigned a, we can turn it into this arithmetic operation, which is secret times a plus 1 minus secret times x, right? And if we look at the control flow graph, this one has an explicit branch, which would potentially leak whether or not we take this branch through the iCache. This one is straight line code. It's doing nothing interesting. It's just arithmetic. and these two are semantically equivalent, right? This one might be a little bit more costly, the one on the right, but it's a worthwhile trade-off, especially for crypto implementations. Okay, and just to give you kind of an idea of like what do we do if we have an if then else, right? This suddenly like is starting to look a little bit more complicated. Well, you end up transforming again. You execute both branches, and you just condition whether or not you assign to X, A, and B based on what the secret is at that particular time. So the question is, are C-style ternary operations safe for this, or are they just as bad as normal if-then branches? So ternary operators, for folks who may not have seen, would be, say, secret, question mark, A, B, and this will give you A or B depending on a secret. So it's essentially a way of doing if statements as expressions. They are as bad, so they typically will get translated into the equivalent if statements that have jumps, and that would leak through the cache. Okay, so how do we? So it kind of seems like optimization by eliminating branches. It's not, because we're actually doing more work, right? Like we're not just eliminating branches. We're doing more work. We're always executing. In this case, right, we're always executing both branches. That's what the right hand side essentially is. It's just like what we store in X depends on the secret, but we can do it in such a way that doesn't leak whether or not we executed this or this, because we executed both. So we are taking a performance hit potentially for security reasons. It's not always clear that this code is going to be much slower than this code, right? Like sometimes straight line code can be pretty fast. But yeah, in general, we for these kinds of things, you are taking a performance hit. But that's kind of the point, right? Like if this thing is faster because of a secret, it's leaking that secret. So are there translator post processors which can transform ordinary code into constant time? Yeah, so we'll talk about that in a little bit. The answer is yes. And performance is overrated. At least, we can talk about performance when you all stop using like Ruby and Node.js. Okay, so there are multiple ways to fold control flow into data flow. I only showed one example. Another way is to use a macro like this one. I forget exactly where I grabbed this. It's some crypto code, but this one, instead of assuming that the secret is 1 or 0, it assumes that the secret is all ones or all zeros, and then uses a slightly different arithmetic expression to essentially do the branching. In a Boolean case, we can do reductions like this. Wouldn't any sort of function call leak nearly as much information? I'm going to avoid taking that question, but basically function calls are themselves like a pretty tricky way of trying to do without leaking. It is doable, but again, the whole idea is your control flow can't depend on secrets. So whether or not you perform the function call can't depend on a secret, which means basically if it does depend on a secret, you have to do it twice. Okay, so let's look through one particular example. So the thing that we're going to look at is an example from Embed TLS, which is a TLS implementation for embedded devices. We'll see more of these kinds of things in the crypto classes, but the basic idea, it doesn't really matter like what it's actually doing. The thing that we're going to look at is this particular implementation that removes padding from a buffer. So we have this like long buffer. The buffer's length is secret, and it contains secret information of secret length, and there is an amount of padding to make it fit within some alignment boundary, like let's say 64 bytes or whatever. Okay, so we're gonna try to actually implement this piece of code. This is what the code looks like or looked like at some point. I'm going to ignore this particular bit here. It doesn't really matter on the weird C. This might be a null pointer. Okay, so here I have my my input, and I have my input length, which is going to be different from the data length, which is the length that the secret length at the end of the day, right? So my question to you is this piece of code safe or not? Right? Does it leak the length of this secret part of the buffer? Does yes mean not safe, or does yes mean yes safe? Right. So this is not safe, right? So like, why is it not safe? Well, here, if we're looking at what's going on, well, we're looking at the buffer contents, right? Whatever I minus one is. And then we're saying if that thing is not zero, we're going to set the data length to that I, and then we're going to terminate early, right? So we're basically not going to go through the whole buffer. We're going to stop basically once we're done with the padding, right? And here, for folks who didn't fully catch the way this is implemented, we're starting from here and going this way. So basically, that first implementation would have stopped at this bit here, right? So definitely not safe. Great, that's leaky. Okay, so what we're going to do is we're going to fix it. We're going to turn that control flow into data flow. So we're going to keep around two bits, done and previously done, and we're going to remove that, if return 0 into this arithmetic operation, and then some if statement with, assigning that length, whether or not we're actually done. Is this safe? Well, this again is not safe. It's a little bit more subtle, but basically this done contains, again, secret information. And again, we're branching on secret information, which means that what we write here is secret. So this, again, might actually leak. What about this piece of code? So I've turned that if into now this CT select macro that I had before. Is this safe? So, okay, what is it doing? Well, it's iterating through the whole buffer from the end up to the first. And then it's just doing a bunch of arithmetic operations. It's not branching on secrets. It's not accessing memory on secrets. This is good to go, right? It's safe because it's the same for like whatever input we choose. Exactly. Okay. So to summarize, the problem with timing channels, or really what we were seeing, I guess, like in this example, is that control flow may depend on secrets. These secrets can introduce leaks. These leaks can be done through loops, through if statements, switches, ternary operators, so on and so forth. Other things that are super bad are go-tos, breaks, continues, basically anything that we love about programming you can't use when you write this kind of code. Even function calls can be pretty bad if not done right. But if you follow the rule of law that control flow that does not depend on secrets, and the way you do that is by essentially folding the control flow into data flow, then we know that your program at least doesn't leak that way. It might leak through not a timing side channel. It might leak just directly. Okay, so we talked largely about control flow. The last one is memory access patterns. And this we kind of like already talked about, but I want to like rehash it because it's worth having these three in your mind when you're thinking about programs that handle secrets. So again, don't use variable timing instructions. Don't use control flow on secrets. Last one is don't access memory based on secret indices, right? So this is part of the AES algorithm that I mentioned a few times. You can see kind of clearly here that parts of the secret K are actually used in some buffer as an index, right? And this basically leaks information through the cache. Now, how do we fix this? We kind of saw how to fix control flow. Well, we basically can't let you access memory at secret locations. There are researchy ways of doing it, but like for real, what people do is they don't access memory based on secrets. So like you could try to compile this array access at some secret index into a for loop that accesses the whole array and that doesn't leak it that way. That would be silly. We don't typically do this. But it is doable if you're trying to like encode arbitrary programs. Okay, so in summary, the duration of the computation can depend on data. We want to avoid those kinds of instructions. We don't want the control flow of the program to depend on secret data because that also leaks through the iCache, and we don't want memory access patterns to depend on secret because that would basically leak through the data cache instead of the iCache. Okay, so the solution and the things that we saw, these transformations, is called constant time programming. It's not actually constant time. It basically just means data independent, right? So the duration of the operation no longer depends on data. And kind of our approach has been to turn control flow into data flow. And if we need memory accesses, into fully accessing the whole buffer, or subsets of the buffer that don't depend on where the bounds don't depend on secrets. Okay. Now I want to briefly just mention that, like, maybe you already got the feel that writing constant time code like this, these transformations, is actually awful. It's really hard to get right because, again, like, we're no longer essentially writing programs, we're writing circuits, and we're writing them in languages like C, which means that we're totally doomed, right? So, just kind of as an example, there was a bug in OpenSSL, which is one of the most popular crypto libraries. In '03, this bug lingered around for a while. This was a bug that they screwed up, like the padding length that we essentially just talked about, or one in that style. Then they fixed it. Turns out that fix introduced another timing channel. They fixed that. That thing introduced another timing channel, and so on and so forth. So writing these things is actually really error prone. Luckily, you generally shouldn't do this, and that's because you generally shouldn't implement crypto, but sometimes you may need to write programs that are independent of secrets, and doing that is pretty tricky. So, for example, it's so tricky that getting it right yourself over and over again has been like an indication that we're bad at thinking about this manually. So what we can do is we can design languages and tools to help us. So one of the things that we did in our group was we built this language that looks like what you're seeing here. So it looks like a mix between C and Rust, and it just has essentially explicit secret annotations that would then let the compiler do the transformations for you. So for example, this is pretty much the code that we saw originally from Embed TLS. We're letting you use returns, we're letting you use branches, but the compiler does transformations for you. So kind of like if we have like a program like this that has ifs and a bunch of assignments, it gets transformed into the gross constant time thing underneath the hood. But the important bit is that you, as the programmer, never have to actually deal with this. So we have a research prototype, but some of you are going to actually go into industry, and if you have to write this kind of code, I encourage you to take some of these ideas and make them fly. Okay, I'm going to skip this slide and get to the last bit of the lecture, which is on Spectre attacks. So this shouldn't take more than a couple of minutes. But if you have to take off, just take off, and then I'll see you. Just watch the rest of this after. Okay, so just a quick review on instruction set architectures and the underlying microarchitecture. Right, so the ISA is basically the interface between hardware and software. This is the thing that you've all had to write programs in, right? The x86 is one ISA. But this ISA is implemented using what's called microarchitecture. So these are kind of the underlying details that we don't expose to programmers. Things like cache-specific details, and how certain instructions are actually like in the microarchitecture implemented using a bunch of like smaller, simpler instructions. Now, the key issue with Spectre attacks, and actually even some of the cache attacks that we talked about, is that the microarchitectural details can become architecturally visible, right? So for example, if I have a stopwatch, I can measure things in the cache. That depends on whether or not some other thing is in the cache. Suddenly I just learned something about the underlying microarchitecture, right? So as much as we'd like for this to be abstract, it's not, and it's something we can measure. Now, the other things before we get to Spectre is instruction pipelining, right? So processors break down instructions into small parts, and they do this because then we can run a bunch of these smaller parts in parallel, right? And this is really a architectural optimizations. So at a high level, at the ISA level, things appear to be executed, one instruction at a time in order. For real, what's going on is we're going to execute a bunch of these things in parallel, and we're going to handle dependencies between who goes first, who goes next, and kind of like what inputs depend on previous outputs underneath the hood. But to you as a programmer, this whole thing ends up being transparent, but again, something potentially visible underneath the hood that may actually leak. Now, I'm briefly going to mention out-of-order execution if you haven't seen this. So the other thing that our processors do is they look at the instruction sequence, and they can actually just start executing instructions out of order. They don't have to do it in order. This avoids kind of pipeline stalls. So when we have our pipeline where we're executing these instructions, and again, it's one of these optimizations that is completely transparent. So to you as the programmer, it looks like things are in order, but it turns out the instruction, like 5 instructions down, was executed before the current instruction. We're not going to talk about the implications of this in this class, but I wanted to bring it up because one of the kind of high-profile attacks, the meltdown attack, actually took advantage of out-of-order execution to bypass permission bit checks on page tables. Right, so this was a hardware bug, but it was kind of in the spirit of out-of-order execution. That's the thing that you need as the attacker to take advantage of. It basically lets you as the attacker read parts of pages that you technically shouldn't be allowed to read. So you can read parts of the kernel as a user space process, and that's pretty scary, right? And it's because we're able to execute instructions in advance and out of order. Okay. Now, the interesting bit that is at the heart of Spectre is speculative execution. So our modern processors are out of order, they're pipeline, and they're speculative, right? So sometimes control flow depends on the output of an earlier instruction. For example, when we get to a conditional branch, that thing, whether we go left or right, depends on previous instructions. You've seen indirect jumps, calls through function pointers, right? Like we have to resolve what that thing actually points to before we jump to it. One way to do this is we just, have a processor that's not speculative. It just waits for you to resolve that branch condition or for you to resolve that function pointer. And then, then it jumps to those locations. What real processors, modern processors do is they just speculate about I don't want to wait. I'm just going to guess that I should go left instead of right because that's what we've done in the past. If I guessed right, that means I just executed a bunch of instructions and that's awesome. I made a lot of progress. If I got it wrong, hopefully this happens very rarely. And indeed, that's kind of the whole hypothesis of these techniques. The microarchitecture kind of scraps this whole thing to you at the ISA level. This is not transparent. So it doesn't look like we took the wrong branch because, we're just going to continue on the right branch once we figured out that we should have gone right instead of left. So to you, again, this all appears in order, correct, but the underlying microarchitecture, did actually go left instead of right. So we totally guessed wrong. And it might have left some state dirty because it took that left instead of that right. And if that state is the cache, we can observe it. So let's actually do this. So here I have a sequence of instructions, right? So again, with out of order execution and speculative execution, I might have my instruction pointer at this level, but underneath the hood, I'm actually, executing already this small instruction. Now, the interesting bit is what happens when I get to a branch. So I get to a branch instruction, and then I can go left or right? So, okay, instead of waiting to figure out, what this branch depends on, which might depend on some instruction from here, right? So it might take a while for me to figure out whether or not to go left or right. What do I do? Well, what I do is I asked my underlying microarchitecture, the underlying predictors in this case, the condition branch predictor to just tell me to go left or right based on information that it's recorded over time, and saw me go left or right a bunch of times. So in this case, if my program kept going left 1,000 times, the predictor kind of remembers that you like going left. So what we're going to do is we're going to execute the left side of the branch. Now, how can we use this as an attacker, right? Where does the Spectre attack come into place? Well, take this piece of code into account. So this is kind of what would be called a Spectre gadget. So here is a piece of code that would appear in lots of programs, right? So what we have is we have two arrays, public A and public B. They both contain public information. And what we would like to do is make sure that we're accessing, public A at address N, and we want to make sure that address N is within bounds, right? So we want to make sure that we're not accessing beyond this boundary of where public A is. And then we're taking the result of this public AN, and we're using that as an index into a separate array public B, and kind of that's it. So this is the gadget that I, as the attacker, if I'm, say, co-located with you in the same process, I would use to try to read some secret information. So how do I do that? Well, okay, let's observe what actually happens here. So if I somehow get your program or get my program as the attacker, so either one works perfectly fine. So I'm going to get this code snippet to always guess true, right? So it's always going to execute these two lines of code. So how do I do that? I basically just call this piece of code with an n that's less than the public length, right? All good. So we're always accessing, public A somewhere here. Okay, cool. So that means we're going to read something from public A plus n. But suppose like after I've trained the branch predictor to take this true, I instead give it a bad n, right? So I give it an n that actually happens to be greater than the length of public A. In particular, it points to some location here, right? Well, my processor is going to think that we're still going to guess true and execute this piece of code. So it starts executing this thing. That thing actually reads from this location here. And that location there might be, outside of my sandbox. It might be the secret key in this process that we're co-located in, right? And now I have this secret. I use this secret as an index into public B. And what does that mean? Well, essentially this memory location, right? This address ends up is actually a secret. That address is revealed in the cache. So I've accessed memory at a secret location, which means now if I have a cache timing attack, I can learn what that secret actually is, right? So I essentially turned that X, which is our secret, into an address. And now, again, all I'm doing is leaking an address, but that address is a secret. Voila, I was able to get and read arbitrary parts of memory. Okay, does this kind of make sense? So it's pretty subtle, but basically you train the predictor, and right, like, so sorry, I should finish up the rest of it. So like, what's actually going to happen, right? The microarchitecture is going to say like, look, like, great, you gave me this n that's way above public length, so I made a mistake executing this thing. So for real, the condition is false, which means that it's going to undo this whole part, but it still accessed memory at this location, which means that this thing was still brought into the cache. And where in the cache that thing is directly visible to the attacker, so they get to learn what that secret actually is. Okay, so for real, we'll then execute the else branch, but that doesn't matter because we already leaked information there. Okay, so again, how to use this as an attacker? Well, we trained the branch to predict true, right? So it's always in bounds. What that means is we're going to like basically always get the processor to try to start executing these things ahead of time when we want to carry out the attack. So how do we do that? Well, in the second step, we execute the branch with a chosen n that's beyond the bounds. The CPU will totally start executing this thing. So it misspeculates, reads the secret data. The secret data is not visible at the ISA level, but it is visible in the cache because we're going to use it as an index to a separate array. The cache is now dirty. We've evicted whatever it was in that particular cache line. So, we're going to have our exfiltration using a standard, prime and probe or whatever you want to exfiltrate that secret from the cache and bring it visible at the ISA level, right? So kind of like take it out of the microarchitecture and bring it to the top. Okay, so that's Spectre. There are really interesting questions around Spectre that folks are looking at, but one open challenge is how do we mitigate Spectre in a way that's efficient, because we can't get rid of speculation, and this seems like a fundamental attack that we're going to have to deal with on existing processors and even future processors. So this is an open challenge to all of you to go think about and do awesome things with. The last bit that I will mention is that there's kind of the dual of Spectre. So right, Spectre basically lets us read outside of protected bounds, so outside of our sandbox. There's a separate attack called Rowhammer that lets you essentially write to arbitrary parts of memory and basically start executing your own code. So this is an example of a fault injection attack that we mentioned at the beginning. But the way it essentially works is you flip a bunch of memory bits and you turn some instructions into other instructions, and then boom, you get to execute arbitrary code in somebody's browser. On the right side here, I have a photo of a different kind of fault injection attack, but it's kind of like in the same spirit, where they induce memory errors in those voting machines that I mentioned before. Okay, So with that, I don't want to take up more time. We're already 10 over. But if you have any questions, I'm happy to stick around. But also, we'll do a section on Monday so we can talk in more detail there. Awesome. Thank you all so much. And you should really go vote if you haven't voted. Please go vote. It's good for you and good for the world.